So good evening, ladies and gentlemen. I'm Ray Walters, a professor here in the School of Physics. Sometimes I try to look like a 1950s rocker, like I do today with my slick back hair, but that's just because of, I'm sure, what you also experienced outside. So welcome to the final talk in this year's July lecture series. I begin proceedings in our customary way by acknowledging the Wurundjeri people as traditional owners of this land. In doing so, I pay respects to the past and present elders of the Kulin nations. Over the past few decades, scientific progress has come to rely on large-scale projects that are usually funded by national governments or indeed groups of governments. That's big science. Individual or small group science, what we can call small science, is still relevant today, and theoretical results, for example, by individuals do have an impact, but often empirical verification requires experiments using big constructions such as the Large Hadron Collider. So that's the topic of today's July lecture. Tonight we'll actually hear about two of these large facilities. First, Elisabetta Barberio will speak about the Large Hadron Collider, and after that, Rachel Webster will give a presentation on the Square Kilometre Array. We'll take questions after they have both spoken for about 20 minutes each. So first we'll hear from Elisabetta Barberio. Just to introduce her briefly, she is an associate professor and reader here at the University of Melbourne. She has a strong international reputation in experimental particle physics. Prior to joining us here in Melbourne in 2004, Elisabetta worked in Europe and the United States. She is a member of the Atlas collaboration at the Large Hadron Collider and led the University of Melbourne team in one of the analyses that showed evidence of a Higgs-like particle. You may have seen some of that in the press 3 weeks ago. She is a chief investigator in the Centre of Excellence for Particle Physics at the Terascale. Please welcome Elisabetta.
Okay, thanks a lot. I will start with the first part of the question, the facility that is the Large Hadron Collider. I think all of you heard about it for many of these public lectures in the newspaper. So, can you hear me? No, yes, sorry. Okay, so we start with from why we have big question. Well, human being has a very curious ways, kind of animals. We climb mountains to see what is above there. We explore the depth of the ocean. We even explore space. We went to the moon, and now we're sending a machine to Mars and also in the solar system to understand what's going on. We also explore the depth of arts, and we had many centuries and millennia of arts. And some of the arts was inspired, most of the arts maybe it was inspired by what the world around us. And in particular, the beautiful picture from of the sky. And the sky inspired us most of the time of what was going on in nature around us. And this not nice sky. Everybody of you, observing the night sky, especially in the southern hemisphere. I come from the northern hemisphere, and the southern hemisphere is really beautiful, the sky, very full of stars, and the hemisphere is not so bright. So asking ourselves wondering about the night sky, and wondering where everything comes from, and all the curiosity we had, we start asking us fundamental question, where everything, the universe comes from, where does that come from, where we come from, where everything that we observe around comes out. And these are the kind of fundamental questions that we start asking ourselves. And they start driving our curiosity. So we start asking where we come from. And we realize by experimental information that we believe that the universe was born 17.7 billion of years ago by an explosion that we call the Big Bang. And the universe has been always expanding since. This is the origin of what we believe would be the origin of our universe. And why do you know that this is like that? Why do we believe that as a theorist? Well, do we know this because of a piece of evidence that light produced is still around and can be observed from the beginning, from the very ancient time, and at the beginning was Perez and Wilson discovered in '64 as a background noise on their radio telescope. Radio telescope was the beginning of our understanding where we come from and of the Big Bang. Now, how do we study what's happening at the Big Bang and at the beginning of the universe and how the universe evolved? Here there is a picture of the Big Bang. Here what's happening real at the Big Bang, and afterward as the universe started cooling down, the universe was very hot at the beginning and started cooling down, and also the universe was very small at the beginning and started expanding. At the beginning of the expansion, we had quite a bit of particles that we don't have in the universe today, and as the universe cooled down, we start forming neutron and proton start forming atoms. And these atoms after start forming the elements. And in this particular part, experimental particle physics, and so I work with accelerator machine, I can think about my accelerator machine as time machine that recreated physics soon after the Big Bang at the macroscopic level. So as a particle physics, I observe this part of the universe, that is the universe mapped very, very early, very, very fraction of a nanosecond before, soon after the Big Bang. As astronomers, as Rachel will show you, they start studying the universe as it is now, going back what they call the dark age of the universe. So in a certain sense, the two sciences, particle physics and astronomy, are really complementary. We really study the evolution of the universe in two different regimes. Now, what do we know now about, and in particular the LHC, we are 10 to the minus 12 seconds soon after the Big Bang. And here, where the LHC is now. All the history of particle accelerator in history was moving from this part, that about 10 to the minus 18 second, to 10 to the minus 10 second, to 10 to the minus 12 second. And the idea is to move more and more our knowledge down the track, almost to reach the Big Bang. So what do we know now? What do we learn about accelerator physics and the universe around us? And what was the condition of the universe soon after the Big Bang? We have this picture in which we have fundamental particle, and we have many kinds of fundamental particles. Some particles that we call leptons, some particles that we call quarks. Quarks are the particles that made up proton and neutron, that they made up the nuclei of our atom. And this is the leptons, in which we have the electron, and the electron is part of always our atom. But after, we have also an understanding of fundamental forces at the fundamental level. And we have particles that are responsible of our forces. And in our accelerator physics, particle physics, we studied the strong interaction, the electromagnetic interaction, and the so-called weak interaction. And all of them, we know what they look like at our fundamental level. We have an understanding of gravitational interaction at the large scale. We don't have an understanding of gravitational at the small scale. So this is the picture we have. What is interesting about this picture, that when we look at the universe as it is today, and we look at the matter in the universe, we realize that the matter of the universe is only made of electron and two kinds of quark. Well, while we go back in our condition at the beginning of the universe, we have a much more replica of this quark. We have 6 quark and 3 kinds of electron-like particles plus the neutrino. So we would like to understand why at the beginning of the universe there are so many particles, and eventually when we see the matter that is around us, we only have 2, 3 kinds of particles that make up everything. The other mystery that we try to solve in our question, of the big question on in particle physics, is that when at the beginning of the universe, at the beginning of the Big Bang, we produce matter, what we call antimatter, that is the same property of matter but different charge in equal quantity. But for us to be now, today, and be living in our universe, the antimatter needed to disappear. We do not have any fundamental understanding why this other kind of matter, that is antimatter, disappear in the universe. And this is what we are still trying to understand in particle physics. There is another thing that relates us pretty tight with astronomy, and is that if we look at what is in the universe, we can think of the visible matter of the universe like a tip of an iceberg, and all the rest of the universe is made of something we don't know. In particular, it is 25% of the universe that is made of what we call antimatter. And antimatter is matter, sorry, and that matter is something, sorry. And dark matter is something that we don't know what is about. We don't know what, we know it exists, but we don't know what it is. If this dark matter that we don't know what it is a kind of fundamental particle that we can study in our accelerator, and we particle physicists suspect it is, we may be able to recreate in our accelerator, recreate in the lab, and study. So this is another fundamental question we have. What is made 25% of the universe? Because only 5% of the visible matter is the matter that we know, like it is on Earth. The other question, fundamental question we have is that there is other extra dimension in our universe. There is a lot of questions that can be answered if we assume that there is any extra dimension. The extra dimension will be very, very tiny, and they are not observable at our scale, but will be observable in a particle accelerator. So this is a few of the many fundamental questions that we are trying to answer. And for this fundamental question to be trying to answer, we really need large infrastructure. Because only particle accelerator can explore the tiniest object in the universe, like the quark, the tiniest elements of matter, and reproduce the condition of the universe only a fraction of a nanosecond after the Big Bang. Now, how big this facility needs to be to answer our question? The facility that all of you heard about is the Large Hadron Collider. And just to give you an idea of what do we need to do this kind of experiment, I just give you a range of what are the kind of peculiarity and more importantly, I would say, interesting things of this accelerator. First of all, the accelerator is located between the border between Switzerland and France at CERN, the European Laboratory for High Energy Physics, and is one of the biggest laboratories in the world. The accelerator itself is a 27-kilometer accelerator, 100 meters underground. I think you saw many times, if you saw in the media, this is the Large Hadron Collider. This is just a drawing, and this is the area. Just to give you, it's 27 kilometers underground. This is the airport of Geneva. This is the International Airport of Geneva. Boeing can land in this airport. So you can see how huge it is, 27 kilometers diameter. This is the biggest lab in the world. This is CERN. This is the lab at CERN. This is the real lab, and this is there. Sorry?
Il microfono, scusi, non si può ascoltare bene. Ti prego, scusi. Forgive me, I cannot be. The microphone is not working really well. Sorry.
Okay, I try like that.
Grazie.
In the world fastest, okay, the laboratory, our accelerator is the world fastest and most brutal racetracks. You can see here, we are accelerating. They have several thousand billion of protons that goes around at 27 kilometers per second at 100 meters underground at 99.9999% of the speed of light. And this proton crashing head-on to each other 4 billion of times, 40 million of times a second. So you can imagine how many collisions we have. Sorry. There is a problem with the microphone. I try that now. A time a second. Now, the accelerator where this proton race is one of the most empty space, the empty space in our solar system. In fact, the proton goes around in what we call the beam pipe, in tube, that is evacuated to the same vacuum as the interplanetary space. The pressure is about 1/10 times the surface of the moon. You can imagine what we need to get this going. Now, the next one is that in one of the coldest, we also need to operate in one of the coldest regions of the universe. The LHC is a huge fridge with a temperature that is about 1.9 degrees above the absolute zero. Think about that the universe is about 2.5 degrees above the zero. See, this is one of the coldest region in the universe, is coldest the interstellar space. Not only we needed to do that, we also needed that when we collide our proton, we have also the hottest reaction in our galaxy. And this is one of our reactions when we collide proton. And the beam of proton collide with a tiny volume at temperature that is more than 1 billion of times in the very heart of the sun. So this is the kind of condition we need to have to answer to our big question. Now, not only we needed to build a facility that could get us all these things, we also built the detector. We needed one of the most complex technology ever built. We have a detector that had 140 billion of data channel and observed 40 million of times a second our collision. And after is analyzed what the biggest computer facility in the world that is spread all over the world, that is coming the grid. The amount of data that we need to analyze per second is humongous. This is just an idea of the number of CD that you need to stack. It's 20 kilometer stack of average CD per year, the amount of data that the LHC produced. So when we speak about big facility, we really speak about a huge amount. And after, for this big facility, obviously you can imagine we needed to have a big international collaboration. And we are speaking about 10,000 scientists from all over the world that you can see here, all sitting at CERN. And the CERN is an international laboratory founded by 20 member states, but is hosting all these other countries all over the world. You can see that is almost every continent except Antarctica is represented. In some continents like Europe is fully collaborated. So at the LHC we will have few experiments that will analyze the collision. They are divided, so since 10 times scientists are divided up, these two experiments have most of the scientists. They will have between 3,000 scientists each analyzing the data. And the idea is that we analyze what we get from this collision, and we figure out from what is coming out from the debris of this collision, this kind of particle that can be created and maybe we didn't see before. And as everybody see, from the collision of this accelerator, we found what everybody expects, well, what we expected since 40 years, the well-known Higgs particle, or what we suspect is the Higgs particle. And this is, I think, I'm not going to repeat the big discovery and was all over the news. Now, you can see big facility, you can see big people, you wonder if what is the ability of us as a small group, for example, in Melbourne, to have part of this big facility and big discovery. Well, experiments are so big, 3,000 people, but every team will have its own analysis, will have its own pie to analyze. And just to give you an idea that individuals play a big role in this big facility, is not only will be hidden between these 3,000 people. Here is just a list of PhD, postdoc, and master students from the Melbourne University and COEP that participate to the discovery of the Higgs. So you can see that despite there is a large community, still individuals play a large role. Anyway, this is one of the biggest facilities ever built. People said that the Higgs, the LHC experiments were the biggest enterprise from human after going to the moon. What is next? How do we go next? And this is the game, because still some of the question, we know where the origin of mass of fundamental particle comes from, but still question about dark matter, question about matter-antimatter symmetry, extra dimension need to be answered. So we still have a lot of variety projects, but these projects are going more and more global. In fact, we need global collaboration, And also we need funding over many, many years. It took us 20 years to design and build the LHC. So if we go with this global facility, we need funding all over many years. And we also need to have accelerator in all regions of the world, like in Asia, in Europe, and in the States. It's mandatory, otherwise we lose one of the regions. And, for example, this fact that we really go global, CERN, that is the biggest laboratory in the world and is international, opened the door to every single country, not only European to join, but also, and it's quite important, decide to join any global project independent of the location. So this is really how the field is moving. It's moving bigger and bigger. Not only we have these huge things at CERN, but also CERN is going out of CERN. So, what are the main points to have future choice and road? This is the roadmap that we need to do. We need funding over many, many years. The next facility may be ready 20, 30 years from now. So we need to present and discuss between the international contest before making choice. International contest means that all of us, all over the world, need to decide what to do next. Need to present physics case into account and test results of what exists in facility. To need to present additional benefit to society, because we need to convince government. We are speaking about $billions project. We need to convince the government to pay us and to give us money. And we need to have excellent communication and outreach accompanying a project, because we need to convince you, the taxpayer, that it's worth to invest money in our fundamental research. And so all of these must be go in this big facility. And everything, so society itself is all involved in this big facility. And for this reason, for example, I want to show what the Economist say is July 7, 2012, about the discovery of the Higgs, and about the fact that we paid 10 billion, the project was 10 billion. That was still a relatively small amount to pay for knowing how Higgs really works. And here it says, for non-physicists, the importance of finding the Higgs to belongs to the realm of understanding rather than utility. And this is what, in reality, this kind of big projects are. We really deep go into what is really understanding of the universe and the fundamental question. We have this big facility to answer fundamental question. And this is really where we are going. However, we need to keep having the discussion with society about the benefit of society that is not only fundamental science, but also all the benefit of going and pushing even more the technology. And this is where I think we are in particle physics, to push the boundary and to go even more global. The next project will be a world project, not anymore 650 institutions from all over the world. Maybe we are going to 1,000 institutions from all over the world. And I think now I'm leaving that part to the even more global part that is the SKA project.
Thank you very much, Elisabetta. As I said, we'll have questions right at the end. So now let me introduce our second speaker, who is Professor Rachel Webster. She's the head of the astrophysics group here at the University of Melbourne. And in fact, she was the first astrophysicist employed here in the School of Physics about 20 years ago. So her research covers a range of areas in extragalactic astronomy and cosmology, including gravitational lensing, quasars, the epoch of reionization, which is a technical term. It refers to the epoch where the first stars were formed, and H1 astronomy. Rachel is a chief investigator in the ARC Centre of Excellence for All Sky Astronomy, and has played a major role in the inception and development of the Murchison Wide Field Array, a low-frequency precursor to the Square Kilometre Array, the very large project that she will tell us about now. Rachel is also very active within the University of Melbourne and currently holds the position of Deputy Vice President of the Academic Board. She has also had wide-ranging roles within the international astronomical community. Please welcome Rachel Webster to tell us about the SKA.
just give me a minute while I get organised. Okay, sorry about that. Okay, well, first of all, thank you for coming out tonight. It's a pretty murky night out there, and I hope that you'll enjoy what Elisabetta and I have to tell you about large facilities. So first of all, the thing that you're going to notice is that both Elisabetta and I are talking about very, very similar topics, but at certain points we're going to be coming from quite different directions. So I'm going to primarily talk to you about the SKA, the Square Kilometre Array, which is a project that doesn't actually exist yet, although I'm sure quite a lot of you have heard something about it. So we're about 20 years behind the Large Hadron Collider, but very, very much focused on exactly the same scientific questions. So let me just start with a quote that I came across recently, which I think is a beauty. This is from a guy called Albert Michelson. Some of you may remember the Michelson-Morley experiment, and this guy was doing physics experiments in 1902, and what he said was, the more important fundamental laws and facts of physical sciences have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. Okay, so that was 110 years ago, and I think our colleagues, the particle physicists, have ably demonstrated in the last 3 weeks, as recently, that indeed there is much more to be discovered. And of course that's what these big facilities are aimed at doing. Now, I just wrote down a list of questions that I thought represented some of the biggest challenge questions in physical sciences that we are looking at currently. So, of course, the Higgs boson has to be up there. Let's assume that we've discovered that now, but there's still, my colleagues assure me there's still a lot of work to do to verify and to understand exactly what has been discovered. Of course, dark energy and dark matter are on our shopping list, and I'm not going to really talk about those tonight, but I know many of you have attended lectures here where we've talked in some detail about how we might discover, or at least understand a little more about what these enigmatic particles in the case of dark matter and substance or whatever it is in the case of dark energy. The third question, is there life elsewhere in the universe? This is one that is now exercising astronomers greatly. And of course we're coming at it from trying to discover planets around nearby stars, and in particular planets that might harbour life. So we're primarily looking for Earth-like planets, but of course hopefully our minds are open to anything that we might discover. Can we detect gravitational waves? This is one of the topics that the LIGO experiment is hard on the heels of, and we believe that we're very, very close to the first detection of gravitational waves. And then finally, one that's quite dear to my heart, the history of the universe. Can we actually map out the universe from its earliest times, which is the realm of particle physics, through to the times where we can actually observe photons that will tell us something about how the universe came into being and how it's evolved. And that's from the time of the cosmic microwave background, which Elisabetta spoke about, and then through to the formation of the first stars and to the later times when we see galaxies and other things that we know and love. But, of course, in order to do this, in order to move beyond where we are currently, it means that we've got to push the boundaries. And that's exactly what the square kilometre array is aiming to do, is to push the boundaries in one of the dimensions that we can look at in astronomy, and that's radio astronomy. And so the science case for the square kilometre array covers these 5 areas. And you'll see, and this is the language that's used for the SKA. You know, it's a little bit more flowery perhaps than I've put it in, but the birth of the universe, which is the formation of stars, galaxies, and the role of dark matter and dark energy, the cradle of life, I guess that's the poetic bit, and the search for other planets, Einstein's gravity, which is very much focused on gravitational waves, and those are very much about extreme tests of gravity, and so that will be essentially based around pulsars, around millisecond pulsars and binary pulsars, and looking at the effects that we expect to be able to see and measure in very strong gravitational fields. We then move on to the Dark Ages, and this is the one that I'm particularly interested in, and I'll say a little bit more about this later on, but there's a period in the history of the universe which we do not have access to at the present time. In other words, we can see beyond that time to the cosmic microwave background, which is you know, the most distant time that we get photons from, the time or the place furthest back in time from which photons come. And then there's a period which we call the Dark Ages, and we're unable to see into that part of the history of the universe. You can either call it, we're unable to see into that time of the universe, or we're able to see as far back as that, whichever way you want to look at it. And then when we come out of the Dark Ages, essentially what happens is that the neutral hydrogen that has pervaded the universe is ionized and it becomes transparent, and the universe beyond that point is quite transparent to photons, and so we can actually see the stars and galaxies back to that time. And at the moment, our best telescopes, and these are things like the Hubble Space Telescope, the Gemini telescopes that Australia is a partner in, can look right back to the edge of the Dark Ages, but then basically the fog comes in and we can't see beyond that point. And so what we have to do is to think of particularly clever ways to actually see into that time and to see the birth of the first stars and the first galaxies. And I'll explain in a few minutes one of the ways of doing that. And then the final science topic for the SKA is magnetism, and this is something that hasn't been looked at widely within astrophysics. It's really a new area, and the idea is to understand the origins of these huge magnetic fields that pervade our galaxy, for example, understand what causes those magnetic fields, and to understand the effects of magnetic fields on charged particles such as cosmic rays and so on. So what I'm going to do now is just to give you a little bit of a perspective on these new telescopes. And you know, the idea here is just to show you that over time we have greatly increased our capability of looking out into the night sky. So starting back in about 1550, this is Tycho Brahe, who he didn't use a telescope, but he observed the heavens through Galileo, Herschel, and then these are some of the early telescopes, the 100-inch at Mount Wilson, 200-inch at Mount Palomar, and then this is our biggest optical facility currently, which is the Very Large Telescope run by the Europeans in Chile. And you can see that the scale as we go up, this is measured in a very unusual unit called eyes. But anyway, there was two, I beg your pardon, eyes here, and you can see that by the time we get up to the VLT, that we're looking at, what is that, 10 million eyes. So, as I say, a somewhat unusual unit. Those are primarily optical telescopes, but we can do a very similar plot in the radio, which is what we're talking about here today. But this starts much later. It starts in about 1940 with Grove-Raber. So this is around the time of the Second World War. And I'm sure most of you know that the explosion in radio astronomy was in fact due to the Second World War. So it was the use of radar during the Second World War that really developed the technology. And you'll see somebody's conveniently drawn a line in here, but these are some of the bigger telescopes, telescope facilities. There's Parkes here, there's our Australian telescope compact array here, and the SKA is sitting up here, and with an optimistic prior to 2020 date on it, so I guess that's not going to be realised. But this is log of sensitivity, which you could read as collecting area, if you like, and so you can see again that this is going up logarithmically. So what is the SKA? What sort of telescope is it? Well, it's actually an extremely ambitious telescope, and the basic idea was to construct a radio telescope with a square kilometre of collecting area. And so if you think of Parkes, which is 64 metres across, and compare it to a square kilometre, you can see that there's a huge difference. But the square kilometre is not just to be located in one place, but it was to be distributed. In other words, it was to be an interferometer, and the full baseline is to be about 3,000 kilometres, which is roughly the size of Australia or a substantial part of South Africa, which is where it's mooted to go. Now, there is also another dimension though. There's collecting area, there's the distribution of the dishes over very long baselines, but there's also a range of frequencies that this telescope had to collect at. And the frequencies range from 70 megahertz right the way through to about 25 gigahertz. So it's in fact a huge range of observing frequency. And because of that, it is not possible just to build one sort of antenna to collect all of those radio waves. They range from about 4 metres to about 1 centimetre. And so, in fact, you have to have different technologies to collect the radio waves at different wavelengths. And so this is the technology for the very long wavelengths, so the meter type wavelengths. And then as you go to higher frequency and shorter wavelengths, then you need a smoother dish with a better reflecting surface. And you can see these are sort of just schematics of how they're expected to be laid out, but quite deep concentrations of collecting tiles sort of laid out over large areas of the landscape. Now, it is an international mega project of the sort that Elisabetta was talking about, and it's expected that most of the countries that are coloured in yellow will be part of this project. So about 20 countries. I note that the US is coloured in yellow here as being part of this. They've certainly been members of the US community, have been very active in the SKA, but the US has decided that they won't join the SKA until at least 2020, so that has been part of their remit. At the moment there are 9 paid up members and there's 2 more in the process of signing up. But this is a massive operation, and you can see here it's estimated it'll need about $200 million a year to actually run the SKA when it's fully constructed. But on the other hand, the lifetime is around about 50 years, so it will be a massive project. Now, the really key thing about the SKA, I've just shown you some pictures of dishes and feeds and aperture arrays. In fact, the hardware that goes with the SKA, for the most part, is not amazingly new. It's technology that we're reasonably familiar with. There are a few new technological developments which I'll point out in a moment, but the SKA is really about massive data rates. The sort of data that's going to come off this telescope is scary even for the particle physicists. And that's actually saying something. Signal transport. Now, the first thing I want to do is to go down the bottom here and just remind you, when you look at these powers of 10, most of you are familiar now with gigas. That's 10 to the 9 because you probably bought one of those little discs or something that's got gigabytes of storage. Tera is when we go up by another 3 orders of magnitude to 10 to the 12, and you may even have found a disk with a terabyte of storage on it. Peta is another 3 beyond that, and exa is 10 to the 18. So when we go from giga to exa, we're basically talking, it's 1 billion times 1 billion bytes. So we're going up a lot of orders of magnitude. And what you'll see if you look through here, data storage, an exabyte, and that's not the sort of one that you buy, but it's this sort of capacity, okay? High performance computing, exaflop capacity, okay? And signal transport at 10 petabits a second, okay? So these are extraordinary data rates, and really this is where our challenge is going to be. Okay, so let's quickly move on. Where are we going to build this thing? Well, initially there were 4 candidate sites. We were looking at something a long way from radio interference, had to be flat, dry, geologically stable, good global location, and then, you know, some good sociological and economic characteristics of the country. And of course, we all thought that Australia had all of these things. The site decision, which came through about in May, was in fact something that has changed, you know, the way that the SKA will be structured. There will be 2 phases in the SKA, a phase 1 and a phase 2. Phase 1 is basically 10% of the SKA, so we're basically going for a small bite first, and then we'll build out. It's supposed to be built between 2016 and 2020 for about 350 million euros. Phase 2 will start before the end of that and will cost about $1 billion. To be honest, I think these costs are a little optimistic. I would multiply them by 2 immediately, and it's quite possibly a little higher than that. But this is where it got to be very interesting. The idea was to put all of these facilities on one site, but when it came down to making the decision, so much money and effort had already been spent both in Australia and South Africa, which were the last 2 competing sites, that they decided it would be inopportune to put it in one place or the other, and that they would divide the telescope between the 2 sites. So the low-frequency telescope will come to Australia. The mid-frequency telescope will go to South Africa. And then there's a mid-frequency survey telescope, which will expand the existing facilities in Australia, which will go to Australia. And this is a new element that hadn't been talked about before. Of course, the allocations of the phase 2 build-out will be subject to the sites in question actually getting their act together and doing it properly. So when I talk about radio quiet, just how quiet does it have to be? Well, here's an absolutely wonderful analogue. That's a snowflake. Well, it's a big picture of a very little snowflake. And the energy of that falling snowflake is less than 30 microjoules. So, I mean, you can kind of imagine what a falling snowflake would be like. If we take all the energy collected by all the radio telescopes in the last 70 years, it is less than that amount of energy. Okay? So this is just to give you a little bit of a feel for the regime that we're operating in. It's quite difficult. So the site in Australia is at a place called Bullardy Homestead, or we call it the Murchison Radio Astronomy Observatory. It's about 350 k's from Geraldton. You can sort of see northeast of Geraldton. There's an area here about the size of Great Britain in which 100 people live, just to give you some idea. It's very remote. It's very beautiful as well, but the radio quietness is a key part of it. And this gives you some idea of just how radio quiet it is. If we take our collectors and sit them in Sydney, this is what we collect across the radio spectrum. So this is basically the FM band here, but you can see there's a fair bit going on in Sydney. If we go to Narrabri, which is where the Australia Telescope Compact Array is, it's still pretty ugly, okay? And you can see that quite often our observations are impacted by what's going on around us. This is Bullardy, okay? Population 4, okay? So you sort of see, but you can see down in this regime, which is the place that I really care about, and this is where the FM radio band is, there's nothing there. And that's just because there are no people there. Okay, so this is the huge attraction of the site. So I'm going to show you now two of the pathfinders currently on the site, and just very quickly tell you a little bit about what they're doing. So in the background you'll see some images of the site. This is one of the telescopes in the Australia Square Kilometre Array Pathfinder. So this is a mid-frequency telescope. telescope. It has 36 regular dishes, but the revolutionary thing is this, what we call it a path, which is up. It's the element that's receiving the radio waves, and you'll see it looks like a checkerboard. So instead of the sort of single aperture that you're used to seeing on a radio telescope, it has, it's almost like a CCD pixelated array, and each of those pixels, in fact, will receive a radio signal. So suddenly we're able to multiplex and do images directly. So that's the huge technological advance that we've made with the radio dishes. These are some of the radio dishes. They're kind of cute, 15-metre radio dishes, built for us by our Chinese colleagues, who, of course, were able to build them for half the price of anybody else. And I just wanted to show you at least one lovely picture of a radio galaxy. This is SKA, which is, it's one of our nearest and most extensive radio galaxies. Huge black hole at the centre of it. But the interesting thing about this image, you'll see that it's very extended, and this is a very detailed image. And it was put together with mosaicing at the Australia Telescope Compact Array with 1,200 hours of observing time over several years. And that image we will be able to do with ASCAP in the first 5 minutes that we turn the telescope on, just to give you some idea. In the first 6 hours that ASCAP operates, it will collect more data than all the telescopes, radio telescopes in the world have collected in 17 years. So the data rates that we're dealing with, are going to be dealing with, are scary. Now, you might think we're now going from the sublime to the ridiculous. This is our low-frequency telescope. And these are the elements that actually collect the radio waves. So we call these tiles, and you'll see they have on them what we call bow ties. So these are these little metal things here. This is a graduate student who built it. That was part of his PhD. He's at MIT and he's just passed with flying colours and done an absolutely superb job. But the telescope, the low-frequency telescope we're building on this site, which is called the MWA, has 128 of these tiles. The data rate of this telescope is approximately 1 gigabyte a second. It's the same as the data rate that, well, Elisabetta just told you she was going to have 700 megabytes a second. So our data rate of this very primitive-looking telescope will be greater than the LHC, just to put it in perspective. We expect to turn this on after Christmas. And what we want to do is to map, well, we won't actually map, it'll be a statistical detection, but we'll look into this period of the Dark Ages, and we're going to try and see if we can see the first stars. Now, what we already know with our testing is that we have the sensitivity to see this, which has got us really excited, because there's a big prize on this. But what we don't know yet is whether the systematics will kill us. So, my last slide. I was up there recently. You can see we were being well looked after. And this is an image of the site. And I just want to show you, so these are the ASCAP telescopes. There's little white dots here. You can see them dotted around. It's a very beautiful site. This slightly bigger white dot is the control building. The control building has no windows. The doors look like a submarine. It's got metal walls. It's got 89 dBs of shielding around it, so no RFI can get out. And inside that building is another metal box with 89 dBs of shielding, making a total of nearly 180 dBs of shielding, and that's where the supercomputer will be. The supercomputer for the MWA is GPU enhanced. It's the only way we can do the data. In fact, we will be collecting quite a lot of data, but to first order, it's so much data we can't collect it, so we have to process it in real time. And some of you may be able to see there's a line here. This is where the MWA will be, and there's optical fibre that runs all the way across this building. And the final thing that I just want to say about this building, because it sort of touches on something else that's near and dear to my heart, that you may be able to see that there's no vegetation in this area here. And one of the challenges has been to get electricity to this site. As you might imagine, there's not a power station very nearby. And part of the solution, it's only part of the solution, has been to drill 96 150-metre deep holes in this area here and to run water, a geothermal cooling system through that field, and so the supercomputer is cooled by water run by a geothermal system, not using electricity at all, so it basically comes for free. And so that's basically what we're trying to do.
Okay, thank you very much, Rachel. I'll now invite Elisabetta also to come back to the stage and open up the proceedings for questions and hopefully also some answers. Maybe we can get some lights.
Yeah.
Nice. Okay, questions?
Yeah, for Rachel. They're trying to decrease the noise, obviously, at the SKA area. How do they plan to transport the data?
Okay, optical fibre. Okay, so, well, it's not about decreasing the noise because we hope that there's no RFI there at all, right? But what we want to do is not add to it, okay? So, essentially, we use optical fibre to transport the data, okay? And anything, any of the receivers or anything else are in absolutely, RFI type boxes, but it's optical fibre. So, there's a huge optical fibre bundle that runs from the site to Geraldton. And, bless this current government, the first bit of the NBN went in, then from Perth to Geraldton.
Other questions over there?
Yes.
Yes, you.
Me?
Yes.
Oh, thank you.
Elisabetta, yes.
You mentioned earlier about the possibility of detecting dark matter.
Yes.
I think it was at the LHC or was it the next generation? I'm not sure which, but it sounded to me like we should think, as I understand it, dark matter doesn't interact with anything else except light gravity. So how would you detect such a particle?
Yes, we know how to detect because it is like a neutrino. We can think of dark matter as a neutrino, and in our particle detector, neutrino escape detection, so we cannot see. However, we know that we can conserve, when we collide proton and proton, or proton and antiproton, we conserve energy. And so if we have a particle, and energy becomes mass. And so if we create a mass, and after this particle escape detection, we know that energy is not conserved. And we know if energy is not conserved, something has been produced that we could not see. And since we know that the neutrino has a little mass, we have technology, we can do, using the kinematics of the events, infer the fact that maybe we created something that is not a neutrino that escaped detection. So we don't know what dark matter is. We have, Ray is a theorist, he can give you thousands of models that can tell you that what can be. Rachel had this stake.
I'm impressed, thousands.
I'm always impressed how many models theorists come up with. But this is what we think, our way of seeing it. And if we can have it in the lab, we can study. But nothing, this is our take as particle physicists. It's a different approach of solving the same problem.
May I add my 2 cents worth? So we have to hope that dark matter also has interactions that are not gravitational. If dark matter only interacts with ordinary matter gravitationally, we'll never learn very much about what it actually is.
Be in the dark.
At the back there? Yes. Yes, you.
You mentioned, there was mentioned on not only tonight but other lectures, that the Large Hadron Collider basically involves 2 proton beams. Why has proton beams been chosen rather than any other type of beam in order for them to collide with form particles? And why is it that the particles that are to be discovered close to the time of soon after the Big Bang? Why is it the 2 proton beams? What is it so special about proton beams that can deliver all these answers?
Okay, so when we do particle accelerator, we need particles that live very long because we need to accelerate them and keep in track for a long time. So proton and electron are the particle of choice. Obviously, no matter how you can read in science fiction movie, creating antimatter costs a lot of energy. So if we want to have a big amount of collision created, it's better to collide matter with matter. So that's why we choose proton and proton. Proton and antiproton can be a valid solution, has been used in Tevatron in the USA, but the luminosity, so the amount of collision has never been very, very high because the antimatter costs a lot. So we decide to go, for many physical reasons, proton, because the kind of regime we are going to create, we are going to probe, is okay to collide this kind of particle. The other was right about
The Big Bang. Why is
the
it-
Big Bang. Okay. What we say when we say the particle accelerator reproduced the condition of the Big Bang, we reproduce the energy density that there was at the beginning. So we have enough energy to produce the particle that existed at the time, that now they don't exist anymore in our universe as it is. That's what we say. We're not creating another Big Bang.
A question about the square kilometre array. The very high data rates you need, can you achieve those with off-the-shelf hardware, or are you going to have to develop your own communications protocols and hardware?
It has to be processed by a computer, right? And so the question is, how do we get enough computer power to actually do that processing? And there don't exist computers at the moment that can do the square kilometre array. Okay. As I said before, our small 128 tile array, we've got about 64 GPU enhanced cores, and that will be sufficient. We have 8 seconds in which to sufficiently reduce the data rate to pass it further down the system, and we've been able to do that. Okay, so we can do enough analysis in 8 seconds before the next lot of data comes to actually have a stable system. When we go to phase 1, so this is not phase 2, the 10%, we're going to be looking at about 5,000 tiles. So we're going up by about a factor of 40. That's a lot because this is an interferometer, and so the number of baselines goes up by that square. So that's starting to look like quite a tough ask.
Are you developing your own software to handle
Oh
those?
yes, no, we write all our own software, but we rely. We don't have the capacity to develop new computing solutions. We have to use computing solutions that are commercially available. And I will say, one wonderful thing about the gaming industry is that GPUs works. So that's made a huge difference, and it's not something that we could have done. So,
And what language do you use to program in?
well, it depends.
Okay.
Actually, so the GPUs are programmed in their own language,
Yes.
right? So different bits of the system are basically written in whatever's appropriate.
Other questions? Yes.
When you look at the Hubble deep field picture, you see a lot of galaxies. What happens if we try and look further distant, we go back to the dark ages? What do you see then? You can't see anything behind the galaxies in the deep field.
Okay, so what happens is that when you get to the dark ages, the hydrogen, the neutral hydrogen that formed I think the most distant objects now are a redshift of just over 7, okay? And so that tells you how much the light has been redshifted by. But there's not many objects at that redshift.
In the red?
What's the future now with the LHC experiments? Where are the next experiments headed?
Okay, the LHC I think will run for the next 20 years. There is still a lot to do and a lot of data. When we build this big facility, it's also, Rachel said, we don't do for 1 year, they're really long-term facility. The next one, well, we see something about 125. We need to see if it's really the Higgs. The LHC cannot answer the question. The most recent, well, it's an idea that was circulating since a long time, is what we call the linear collider. The most probable place to be built will be in Japan. However, we still have a lot of questions to answer. I didn't went there, but there is all neutrino physics. We need to understand why neutrinos have masses, and the Higgs will not explain that. So there is a very rich neutrino experiments facility all over the world that is also starting there, and this will be distributed in the States, in Japan, and in Europe. So the next question is to understand what we really see. Is it the Higgs? So we may need a linear collider. And the next is studying if the dark matter is really a particle, not only the collider, but also other experimental world, and understanding the neutrino and the physics of the neutrino, and this is also there are all over the world. So I would say we are going in two directions of relatively small, when we speak about small facility in particle physics, we speak experiment with about 500 people. You know, it's like, this is the way. At the, I would say, international level, where a few countries, say 10, 12, gets together, and maybe a single nation like Japan or the CERN can contribute and build a facility. And after the next, like the linear collider, that may be the next big machine, we are speaking a facility where not even CERN has the ability to build for many reasons. And we are really going through global. And just right now, the big bosses of the director of all the big high energy physics experiment in the world are discussing what to do next on this big facility. So, but as I say, we need to go global, and this is what I said at the end, and it must be important to understand. This project takes 20, 30 years. We need funding for 10, 20 years. We need to engage funding. We need to engage funding facility. We need to engage the government to fund us for so much, for a longer time. We need to engage not one government, not two governments, sometimes 20, 30. In Atlas, there are 26 different countries. Maybe we go to even more countries, so it's a long, it's a sociological, political, and scientific problem.
Appreciate it, you. You are high educated and academia, and you know what it is. But I think before I go to the question, I have a different question. Why do $8 billion from war? Why do you have scientists or medicine or something like that? I think especially we need to focus this area, not go to $8 billion for kill everybody. I got a question. Usually physics, you know better than me. How can we control space and time? Because a human being can go to past easy, but cannot go to future, because there's one. How can we test empirically and experimentally? Possible this philosophy or science? Thank you. That's pretty
Yeah, I'll take it. So string theory and M theory are very difficult to test directly. At this point, they're quite impossible to test directly. They may remain impossible to test directly for a very, very long time indeed. I think the best that can be achieved is that indirect evidence is gathered that supports this kind of picture for the deepest theory of everything, if that's what you want to call it. And that's kind of why string theory and M theory have such a popularity today. It's because there's a certain line of argumentation based on what we know today that leads you in that direction. So it's not that someone has done an experiment and observed that an electron is actually a little wiggling string. very far from being able to do that. It's that there are indirect lines of evidence that point towards that kind of a picture, at least in the minds of many people. Other questions? Yes?
Wouldn't our universe be the exact opposite to a supermassive black hole?
The exact opposite.
Well, the complementary.
I'm not sure exactly in what sense you mean that.
Well, if our universe is a white hole, could it be fueled by a black hole? Along the Einstein-Rosen bridge.
I don't know. I mean, look, one thing you can say is that if you take a line that of black holes, plot mass against density or something, mass against radius, and the black hole line, the closed universe sits on that line. Okay, so that's one thing you can say. It's not a black hole, okay, but it does sit on that line. There you go.
Thanks, Rachel. Thanks for the question. Yes?
If we're 30.7 billion years old as the universe, how do we manage to get a radius of about 46 billion years, approximately, whatever it is, I'm estimating, isn't a radius of the actual size of the universe? We've only been 30.7 billion years old, and something happens at the speed of light, we'll only get 30.7. How do we get to that?
When we talk about the radius of the universe, we talk about the radius of the observable universe. And so it is literally, if you like, the speed of light times the age, the first order.
How do we get 46 from 13.7?
Well,
60 or whatever it is.
Your numbers, you're talking about light years, and I never think of light years. but that's basically what the radius of the universe is. It's just the speed of light times the age, full stop. That's it. Okay.
So, since the square kilometre array has been split between Australia and South Africa, does that increase your interferometry because you now have the baseline between two countries?
It would be great if you could do that, but unfortunately the curvature of the Earth means that it's quite difficult to observe the same thing from South Africa and Australia at the same time. You require that for an interferometer. So the 3,000 kilometre baseline that I talked about is about the effective limit. You might be able to go to 5, I suppose, but you start to limit the period over which you can sort of observe the same bits of sky. Okay, so unfortunately you can't use both of them and have an effective instrument, but you can enjoy the results of it.
So it's no better.
Well, no. I mean, there's been a lot of discussion about whether there are advantages or disadvantages in the splits up. By splitting by frequency, you're also splitting by technique, and so in some ways you end up building two separate observatories, but they'll be managed jointly.
Okay, this is an interesting discussion, but we're running quite a bit over time. I'll have one final quick question.